Okay, hey guys. So I didn't realize the first time around I didn't have sound on this. So I am overwriting this video with sound. So that's why it might be a little bit disjointed. Oh, I didn't play the video yet. So see, I'm already making mistakes. But anyway, so basically what you're doing in this lab is you're going to be combining crystal violet with, there's crystal violet, that's crystal violet, it's purple color, and you're combining that with the hydroxide ion. And that's going to come together to form CVOH, which is a colorless compound. So basically there's a way you can quantitatively measure color, and that's using a spectrophotometer, using spectroscopy. And basically, so spectroscopy is just a way that you can quantitatively measure color, and I don't know why nothing is coming up. But so you can quantitatively measure color, and when you quantitatively measure color, you get, so basically color has different wavelengths. You can see that's kind of like maybe a purple wavelength. The wavelengths are super short together, are super small and close together, whereas that would be like a red wavelength, and the wavelengths are more spread out. And so when the wavelengths, based on the wavelengths, basically every color has a different wavelength associated with it. So like leaves, they absorb a lot of red light and they reflect a lot of green light. You guys know that. So basically the green wavelengths are more likely to be reflected, whereas like the red wavelengths are more likely to be absorbed. And so basically what you're trying to do is, there's a kind of a spectrum, and hopefully I'll draw that here soon. Oh, there we go. And basically on that spectrum, that's like all the different kinds of wavelengths that a certain pigment, in this case the crystal violet, absorbs. And I actually don't think it's the purple wavelength that the crystal violet is going to be absorbing, because that's what it's reflecting. But anyway, there's some wavelengths that the crystal violet absorbs best, and that'll be based on that peak on that wavelength. And that's the wavelength that you really want to be using your, you want to be measuring using your spectrophotometer, because that's what's the wavelength that's going to change the most as you get less and less crystal violet, so less and less of it will be absorbed. And so I think I'm here gonna draw a graph of the percent absorbance versus over time for specifically this purple wavelength that we chose on the graph above. And basically the thought is, over time it's going to decrease somehow, either logarithmically or linearly, depending on whether on what order the reaction is. But that logarithmic, or that linear or exponential, whatever it is, over time it's going to decrease, because you're getting less and less crystal violet, and more of your crystal violet is changing into that colorless compound. So you also, when you do this, you're doing a percent absorbance. So when you do a percent, you always have to compare it to something. In this case, you're comparing it to ethanol, which is the blank. And so when you blank it, you're saying, okay, we're going to assume that this solution, whatever it is, has 0% absorbance. So like maybe there's a little bit of absorbance from the liquid itself, or from the cuvette. But since all the liquid's in a cuvette, and since all the liquid we know is eventually going to turn colorless, we're using a colorless liquid as our blank. And there's another thing about absorbance that you can use, and that's called the Beer-Lampert law. There we go. So the Beer-Lampert law is the absorptivity is equal to the, I'm not quite sure what E is, times the path length times the concentration. Yeah, so A is basically the reading that the spectrometer gives you. E is the molar absorptivity. That's not something we really need to worry about with this. And B is the cuvette, the path length. So that's going to be the length of the cuvette, which is 1 centimeter. And then the concentration of the crystal violet is what we're trying to determine using this Beer, or could be determined using this Beer-Lampert law. So another thing, so ultimately we want to find what the rate law for the conversion of crystal violet and hydroxide ion to that colorless compound is. So we're trying to find these the orders of the reactions. And that can be, remember when we find the orders, we'll want to graph it. A zero order, if you graph a zero order, it will have a negative slope, and it will be the concentration of A, or whatever compound you're interested in, on the y-axis over time on the x-axis. For a first order, it will also have a negative slope, but instead of the concentration on the y-axis, it'll be the natural log of the concentration on the y-axis, and time on the x-axis. And then for a second order equation, that's going to have a positive slope, and it is going to have 1 over the concentration of A on the y-axis. Yeah, so sorry I didn't have the sound uploaded at first, but hopefully you guys can manage. Let me know if you have any questions as soon as I get the data for... Bye.